Hello friends, in first lecture I have explained first principle of derivative, that is definition of derivative, then geometrical meaning of derivative, and I am revising that definition. A function f is differentiable at a, then derivative of f at a is f dash a equal to limit x tends to a of fx minus f divided by x minus a, and we know that limit exists if and only left hand limit is equal to right hand limit. So for that, right hand derivative of f at a is f dash plus a is equal to limit x tends to a plus fx minus f divided by x minus a. Left hand derivative of f at a is f dash minus a is limit extending to a minus fx minus f divided by x minus a, and if a differentiable at a, if and only f dash a plus is same as f dash a minus. Okay, so we'll take examples from exercises. So determine whether following functions are differentiable at 0. Let fx is equal to x square if x greater than or equal 0, and it is minus x square if x less than 0. Discuss delta of f at 0. Discuss differentiability of f or ability of f at x is equal to 0. Solution. So here on the right part of x, means right hand side of x, fx is x square, and on the left side of x, fx is minus x square. Fx is minus x square. Is it right? So if I take here fx is equal to x square, x greater than or equal 0, and minus x square, x less than 0, which implies f of 0. For x greater than or equal 0, x square at x equal to 0 gives value 0. So you have to obtain f of 0 by expression x square. Okay, f dash plus 0 is equal to limit x tends to 0 plus x approaches to 0 from right side, fx minus fa divided by x minus a, which is equal to limit x tends to a plus 0 plus, on the right side of 0 fx takes x square and f of 0 is 0 upon x minus 0, which is limit x tends to 0 plus of x, right, since x not equal to 0. Since x not equal to 0, f dash of minus 0 is equal to limit x tends to 0 minus fx minus fa of x minus a, which is equal to, here, yes, 0, 0, 0, 0. Limit x tends to 0 minus fx is minus x square minus 0 upon x, which is equal to limit x tends to 0 minus x, which is 0. Okay, which implies therefore f dash of plus 0 is same as f dash minus 0 is 0, and this implies f dash 0 is equal to f dash plus 0 is equal to f dash minus 0 is 0. Is it right? Next example. Let fx equal to mod x. Okay, x belongs to R. is f differentiable at x equal to 0? Question mark. So what this implies? Therefore f is differentiable at 0 and f dash 0 is 0. Okay. Next example is fx equal to mod x. Okay. So solution. Here fx is equal to mod x. So by definition of mod x, it is nothing but x if x greater or equal 0 and minus x if x less than 0, which implies f0 is 0. f0 is 0. Okay. Now on right side of x, fx takes x, for left side of 0, fx takes minus x. And therefore, there is possibility of getting different limits for left hand derivative and right hand derivative. So, we have to evaluate left hand derivative and right hand derivative. So, by definition, f dash plus 0 is equal to limit x tends to 0 plus fx minus f0 upon x minus 0, which is equal to limit x tends to 0 plus x minus 0 upon x minus 0, which is limit x tends to 1. Limit x tends to 0 of 1 is 1, since x not equal to 0. Okay, so that's why I can cancel x there. F dash of minus 0 is equal to limit x tends to 0 minus fx minus f0 upon x minus 0, which is limit x tends to 0 minus of minus x minus 0 upon x, right? So what we'll get here, which is equal to limit x tends to 0 minus of minus 1 is equal to minus 1, since x not equal to 0. X is near to 0 but not exactly 0. Okay, which implies f dash plus 0 not equal to f dash minus 0, and therefore f is not differentiable at, or f dash 0 doesn't exist. F dash 0 doesn't exist. Is it clear? Next example, we'll take the simple possible example. Here, let fx equal to say x into sine of 1 by x not equal to 0, f0 is equal to 0. Is f differentiable at x equal to 0? Question mark. Solution. So here fx is equal to x sine 1 by x not equal to 0, and f0 is 0. Now here on left side of 0 and right side of 0, fx takes same expression x into sine of 1 by x into sine of 1 by x. Okay, so now for now limit x tends to 0 of fx minus f0 upon x minus 0 is equal to, I don't know whether limit exists or not, is equal to limit x tends to 0 of x sin 1 by x minus 0 upon x. So this x will get cancelled since x not equal to 0, which is equal to limit x tends to 0 of sin 1 by x doesn't exist. So by sequential limit concept, you can verify that you can find two sequences or a sequence which converges to 0, but f of sin of 1 by x, sin of 1 upon xn doesn't converge to f of 0, doesn't converge to f of 0. Is it clear? So while this limit doesn't exist, you have to check it. Okay, that is I have marked it as question mark here. Okay, doesn't exist. Okay, so for this, there exist sequences. Say xn is equal to 1 upon n pi and yn is equal to 1 upon 2n minus 1 pi by 2, n belongs to n. Yn such that limit x tends to infinity of xn is equal to 0, which is equal to limit of yn. As an approach to this, but limit n tends to infinity of f of xn is equal to limit n tends to infinity of sin of 1 upon xn, which is limit n tends to infinity of xn is 1 upon n pi, means sin n pi, and we know that sin n pi is 0, since sin n pi 0, right? And limit n tends to infinity of f of yn is equal to limit n tends to infinity of sin of 1 upon yn, which is equal to limit n tends to infinity of sin of 2n minus 1 pi by 2, which is nothing but here I'll take instead of 2n minus 1, if I take 4n minus 1 pi by 2, 4n minus 1 pi by 2, okay. So if I put n equal to 1, I will get sin of 3 pi by 2. Then n equal to 2, I will get 7 pi by 2. Yes, 3, then, so this is nothing but minus 1, since sin of 2n minus 1 pi by 2 is equal to minus 1 raised to n. Okay. So this will become 2 into 2n, okay, minus 1 raised to 2n, which is 1. So this is 2 times 2n, okay. So thus limit of xn is equal to limit of yn as n tends to infinity is 0, but limit n tends to infinity of f of xn not equal to limit of f of yn. And therefore by sequential limit theorem, limit x tends to 0, g of xn, g of yn, here I will take instead of g here, okay. What is my g? G is this function, okay, where gx is sine of 1 by x not equal to 0. This is my function. So by sequential limit theorem, limit x tends to 0 of gx is equal to limit x tends to 0 of sine of 1 by x doesn't exist. Is it clear? So this is the solution for this example. Is it clear? And therefore limit x tends to 0 of fx minus f0 upon x minus 0 which is equal to limit x tends to 0 of gx doesn't exist, and therefore f is not differentiable at x equal to 0. It is not differentiable at x is equal to 0. Now here if I take say x square into sine 1 by x square into sine 1 by x, then is f differentiable at x equal to 0? That you have to check. Okay. So here I will get x square, right? Here I will get x square. So 1x will get cancelled here. I will get x into sine of 1 by x. This is my third example. Which is equal to zero, which is equal to 0. Since minus 0 less equal mod of x into sine 1 by x less equal mod x implies 0 less equal limit x tends to 0 of x sine 1 by x or mod x less equal limit x tends to 0 of mod x is 0, which implies limit x tends to 0 of mod x sine 1 by x must be 0, and therefore limit x tends to 0 of x sine 1 by x is 0. Okay, so this limit exists, right? Therefore f dash 0 is equal to 0 exists. 0 exists. Okay. So depending on this, I am giving exercise. Let fx equal to say x into cos 1 by x x not equal to 0, f0 is equal to 0, so that f is not differentiable at x is 0. Next example, let fx is equal to, say, x square into cos of 1 by x not equal to 0, and it is f0 is 0, so that f dash 0 is equal to 0. F dash 0 is equal to 0. So, with the discussion, we'll stop here. Thanks for listening lecture carefully. Bye bye.